So, what we have seen so far is the following. We have looked at what was a random variable, we defined what was a random variable, and then we looked at the types of random variable. Namely, we said that there are two main types of a random variable. We can classify them as discrete random variable and continuous random variables. Then we looked at, when we focused we restricted our focus only to discrete random variables. In discrete random variables, we defined what was a probability mass function in the sense that you are interested in knowing about a distribution of a random variable. Hence, we introduced the notion of a probability mass function. The probability mass function tells us about the probability distribution of a random variable, and the cumulative distribution function helps us to know what is the overall distribution of the random variable given a real line. So, we also looked at the graphs of both the probability mass function and the cumulative distribution function. Then we went on to introduce an extremely important notion of a random variable, namely the expectation of a random variable. We focused on properties of a random variable, and then afterwards we looked at how we can compute the expectation of functions of a random variable. Today we are going to focus on another important summary of a random variable, which we refer to as a variance of a random variable. So, let us first of all motivate the need for such a measure. So, we saw that we also realized that we can interpret the expected value as a long run average. So, in other words, the way we introduced the expected value of a random variable was as a weighted average of possible values a random variable can take. In other words, if x can take values x1, x2, xn, I am assuming finitely many, with probability x equal to xi equal to p1, p2, pn. These are, I assume p1, p2, pn are the weights given to the values. Then I know that the expectation of x can be written as p1 x1 plus p2 x2 plus pn xn. In other words, it is x is taking possible values x1, x2 to xn with weights p1, p2 to pn. Then expectation of x can be expressed as a weighted average of the possible values of random variable. Now, let us look at an example where I have three random variables. So, what are these three random variables? X is a random variable with probability 1. Y is a random variable which takes the values -2 with probability half and +2 with probability half, and Z is a random variable which takes the value -20 with probability half and +20 with probability half. Now, if you compute x, I can write x takes the value 0 with probability x equal to I equal to 1, which gives me the expectation of x is 0 into 1, which is equal to 0. Similarly, I know y takes the value -2 and +2 with probability y equal to I equal to half and half, giving me expectation of y equal to -2 into half plus 2 into half, which is again a 0. Z takes the value -20 and 20 with probability z equal to I is again half and half, which gives me expectation of z, which is equal to -20 into half plus 20 into half, which is again 0. So, I can see that expectation of x equals expectation of y equals expectation of z. So, this expected value, however, what we notice is, though the expectation is same, the distribution of these random variables in the terms of the values they take is different. In other words, the expected value of a random variable does not tell us anything about the spread or the variation. Hence, I need a measure for the spread. What I can notice here although is the spread of z is greater than the spread of y, which is greater than the spread of x. The expected value, although was the same, expected value of x equal to expected value of y equal to expected value of z, which is equal to 0. Hence, I need a measure of spread. And just as what we did in our descriptive statistics module, mean gave us a measure of central tendency, variance gave us a measure of spread. So, we are going to define the variance of a random variable, which is a measure of spread. So, how do I define the variance of a random variable? So, let me denote the expected value of a random variable by the Greek alphabet mu, that is expectation of x is equal to mu. X is my random variable. I see how far is x from mu. I take the square of the difference and the expected value of the squared difference, and that is what I am going to define as my variance of x. So, if x is a random variable with expected value mu, then the variance of x is defined by expectation of x minus mu whole square. In other words, the variance of a random variable defines the square of the difference of the random variable from its mean on an average. I repeat, the variance of a random variable measures the difference of the random variable from its mean. So, that is x minus mu. It measures the square of the difference, which is x minus mu whole square. On an average is expectation of x minus mu whole square. So, when I talk about x minus mu whole square, the question is, can I computationally have a more convenient formula to compute the variance of a random variable? I know variance of a random variable is expectation of x minus mu whole square. Now, let's look at x minus mu whole square. I know x minus mu whole square is x square plus mu square minus 2 times mu into x. Now, recall from my expectation or properties of expectation of ax plus b, where a and b are constants, is a times expectation of x plus b. Okay. So, mu is a constant here. So, if when I am looking at expectation of x minus mu whole square, I know this is equal to expectation of x square plus mu square minus 2 times mu of x, which I can write it as expectation of x square plus expectation of mu square is going to be mu square minus 2 mu times expectation of x. I know expectation of x is a mu, hence this reduces to expectation of x square plus mu square minus 2 mu into mu, which gives me expectation of x square minus mu square. So, the computational formula for x is a very simple formula, which is the same as variance of x is expectation of x square minus mu square, where mu is expectation of x. So, now let's apply this formula to compute the variance of the random variables which we have discussed earlier. Let's begin with the roll of a fair die, and I'm rolling it once. I know the sample space is 1, 2, 3, 4, 5, 6. X is the outcome of the roll. So, my x takes the values 1, 2, 3, 4, 5, 6. I'm going to apply the formula, the computational formula. Variance of x is expectation of x square minus expectation of x whole square, or expectation of x square minus mu square. Okay, that is the formula I am going to apply. So, if x takes the value 1, 2, 3, 4, 5, 6, I know x square takes the value 1 square, 2 square is a 4, 3 square is a 9, 4 square is a 16, 5 square is a 25 and 6 square is a 36. Now, if x takes the value 1, x square takes the value 1 with the same probability. Similarly, if x takes the value 2, x square takes the value 4 with probability 1 by 6. X takes the value 3, x square takes the value 9 with probability 1 by 6, and so forth. X takes the value I, x square takes the value I square with probability 1 by 6. We have already computed expectation of x, and we notice that expectation of x was 3.5. So, what is expectation of x square? X square takes the value 1 with probability 1 by 6, 4 with probability 1 by 6, 9 with probability 1 by 6, 16 with probability 1 by 6, 25 with probability 1 by 6, and 36 with probability 1 by 6, which gives me expectation of x square is 15.167. If expectation of x is 3.5, expectation of x whole square is 3.5 square, and hence my variance of x is 15.167, which is expectation of x square minus mu square, which is 2.917. Similarly, let's look at the example of rolling a dice twice. Again, we know that x takes values 2, 3, 4 up to 12. Hence, x square takes the values 4, 9, 16, 25 up to 144. Again, the probability with which x takes the value 2 is same as the probability with which x takes the value. X square takes the value 4, which is equal to 1 by 6 in this case. And hence, my expectation of x, we have already computed, was 7. I can verify that expectation of x square is 54.833, giving me variance of x is 5.833. So, we notice the following, that in the earlier case, when x was a roll of a die, it took the value 1, 2, 3, 4, 5, 6. It had equal probability. And now you can see that the mean was around 3.5. This was somehow balancing it. Here the mean is at 7. And I can see that the variance in this case is 5.833 because it's taking a value from 2 to 12. So, the variability is more. Here it is taking the value 1 to 6 and it had a variance of about 2.91. Now, let's apply the formula to tossing a coin thrice. Again, I know that x is a random variable which takes the values. Again, I know x is a random variable which takes the values 0, 1, 2, 3. Hence, x square is equal to 0, 1, 4 and 9 with the same probabilities. So, I can verify that expectation of x, I already have checked. Expectation of x was 3 by 2. Expectation of x square is going to be 0 into 1 by 8 plus 1 into 3 by 8 plus 4 into 3 by 8 plus 9 into 1 by 8. That would be my expectation of x square, which I can verify that to be 24 by 8, which is 3. Hence, my variance of x is 3 minus 2.25, which is 0.5, because this is 1.5. 1.5 square is 2.25. Variance of x is 3 minus 2.25, which is a 0.75. Again, you can see that the value of x is between 0 and 3. So, I had, when x took the value 1, 2, 3, 4, 5, 6 with equal probability, I had a variance of 2.91. X took the value 2, 3, 4 up to 12 with varied probabilities. Then I had 5.83. Now, x is again taking the value 0, 1, 2, 3 with probability 1 by 8, 3 by 8, 3 by 8 and 1 by 8. My variance is very less, which is 0.75. So, now let's look at the specific random variables which we have already defined. Recall, we defined a Bernoulli random variable as that random variable which takes only two values. For convenience, I assumed it took the value 0 and 1 with probability x taking value 0 as 1 minus p and value 1 equal to p. If x takes the value 0 and 1, x square also takes the value 0 and 1 with the same probabilities 1 minus p and p. We verified that expectation of x is 0 into 1 minus p plus 1 into 1 minus 1 into plus 1 into p, which gave me the expectation of x equal to p. Expectation of x square is also 0 into 1 minus p plus 1 into p, which is p. Hence, the variance equal to expectation of x square, which is equal to p, minus expectation of x whole square, which is minus p square, which I can write as p into 1 minus p. Hence, the variance of a Bernoulli random variable is p into 1 minus p. So, I can refer to this as if x is a Bernoulli random variable with parameter p, then the expectation of x is p, the variance of x is p into 1 minus p. Let's look at a case of a discrete uniform random variable. Again, I know I call a random variable to be a uniformly distributed random variable if x takes the value 1, 2 up to n with probability 1 by n, 1 by n, 1 by n. Again, an example of this is my roll of a single die where my n was 6 and I knew that probability x equal to each value is 1 by 6, 1 by 6, 1 by 6. So, if x takes these values, then x square takes the value 1, 4 up to n square. The probabilities remain the same. We have already seen the expectation of x equal to 1 into 1 by n plus 2 into 1 by n plus n into 1 by n, which we showed was 1 by n into the sum of the first n natural numbers, which we further saw that this was n into n plus 1 by 2 into 1 by n, which gave me n plus 1 by 2. So, I already verified that expectation of x equal to n plus 1 by 2. Now, when n equal to 6, I know that this is equal to 7 by 2, which is 3.5, and this 3.5 actually matches with my expectation of a single roll of a dice, that is 3.5. Recall, I got a 3.5 when I found out the expectation of rolling a dice one was 3.5. Now, from here, remember the variance was 2.91. So, let's go and check for a discrete random variable. So, again, when I go and do my check for a discrete random variable, I see that what is expectation of x square in this case. Now, if I look at x square takes the value 1 plus 4 plus n square. So, I know expectation of x square, I can write it as 1 by. So, expectation of x square, I can write it as 1 by n into 1 plus 1 by n into 4 plus 1 by n into n square. So, I get 1 by n plus 1 plus 2 square plus 3 square plus n square. The term within the brackets is nothing but the sum of the squares of the first n natural numbers, and we can verify, and we already know that the expectation of n square is nothing but n plus 1 into 2n plus 1 by 6, because the sum of squares is n into n plus 1 into 2n plus 1 by 6. Now, the variance of x is going to be n plus 1 into 2n plus 1 by 6 minus n plus 1 whole square by 4. This is expectation of x square, this is expectation of x whole square, and I can show that this would be, this is going to be a 2n square plus 3n plus 1 minus n square plus 1 plus 2n by 4 by 6, and I can verify that this is going to be a 2n square plus 12n minus 12n cancel out plus 4 minus 6, which is equal to minus 2 by 24, which gives me the fact that variance of x is n square minus 1 by 12. So, we computed the variance of very well known distributions, namely the Bernoulli distribution and the discrete uniform distribution. We will be looking at a few more distributions later, but for now, in summary, we introduce the notion of a variance. The notion of a variance of a random variable captures the measure of spread. Hence, it's an important measure, and we also computed through the computational formula, and by computational formula is variance of x is expectation of x square minus the expectation of x whole square, which is the same as expectation of x square minus mu square. We applied this formula to compute the variance of some well-known distributions and examples that we have already seen.